We're going to cover the last couple sections in Chapter 8 and talk about conservation of energy. Alright, so first let's talk about the work done on a system by an external force. Work is the energy transferred to or from a system by means of an external force acting on that system. Alright, so if you can imagine that we have some sort of system, and the system can include anything. It could be a couple objects, it could be one object, it really just depends on what's interacting. But if you do positive work onto whatever that system is, you're going to give it energy. Right, so when you do positive work, your energy is going to increase. When you do negative work, your energy is going to decrease. So essentially when you do negative work, you're taking energy away from the system. When you do positive work, you're giving it energy. Okay, so we can look at this in two ways. We can look at it if friction is not involved and if friction is involved. Because if friction is involved, then we actually end up losing some energy. But we'll get to, back to that in a second. So let's look at the work done to a system if there's no friction involved. So we're going to start with this equation. Work is going to equal to whatever the change in kinetic energy is plus the change in potential energy, which is essentially saying that the work is equal to the change in mechanical energy. So you can do work on a system. For instance, if you look down here, you have a picture of a bowling ball being raised up. If you apply force, some external force to that bowling ball in the upwards direction, you're going to not only increase its potential energy, right, its gravitational potential energy, but you're also going to increase its kinetic energy as long as the force you're applying is greater than the weight of the object, right? Because if you apply a force that is the same weight of the object, you're just going to be lifting it up at a constant speed. So that's not necessarily going to give it any additional kinetic energy. Of course, maybe that little bit just to get it going at some speed. So if you read the caption down here, it says, the positive work is done on a system of a bowling ball and the earth, causing a change in mechanical energy. The change in kinetic energy is given by delta K, and the change in potential energy is given by delta U. All right, so now let's look at the friction involved scenario. So if you do have friction, and let's go ahead and read the caption down here so we understand the situation. So it says in the first picture here, a block is pulled across a floor by a force F while a kinetic frictional force F opposes that motion. So you have a block being pushed across the floor with some applied force, and we know that the kinetic frictional force is going to be going against motion, so that'll be to the left. The block has some velocity v naught at the start of the displacement, d, and some velocity v at the end of the displacement. Right, and that's shown here. Picture B shows that the positive work W is done on the block force system by some force, resulting in a change in mechanical energy in the block's, a change in mechanical energy and a change in thermal energy. Right, thermal energy is going to be given off from the friction. Mechanical energy is going to be gained because it's gaining some velocity. All right, so if we go to the equations you have up here, we start with Newton's second law. All right, so we start with summation of forces is equal to ma. And we write all the forces that are acting on the block in the horizontal direction. So that's going to be your applied force. This will be the applied. And then we have our kinetic frictional force here. Right, and that's equal to mass times acceleration of the object. So if we take this and we look at the work being done, right, so we look at this force and we say, well, that force over some distance will be the work done. This is going to be equal to the change in kinetic energy plus the frictional force times the distance. Right, so essentially, you're putting in this much work. Right, that's what the applied force is doing. You're losing some of that. So if that's the total amount of work you put in, you're losing some of that to friction, and the rest of that is going into kinetic energy. All right, so that's what we see here in this line. And down here it's just saying, well, really this change in kinetic energy is also the change in mechanical energy. because the change in potential energy is not changing, right? There's no change in potential energy. So you can sort of just equate the two. Okay. So let's go and do a sample problem. In this problem, a food shipper pushes a wood crate of cabbage heads, which have a total mass of 14 kilograms, across a concrete floor with a constant horizontal force of magnitude 40 newtons. Right? So you have this constant force of 40 newtons. In a straight line, displacement of magnitude 0.5 meters. The speed of the crate decreases from 0.6 meters a second to 0.2 meters per second. So how much work is done by the force, and on what system does it do work? All right, so let's look at the key ideas. So because the force F is constant, we can calculate the work it does by simply using work is equal to Ft cosine theta. Right, we don't need to use the integral form here because the work is constant. So we'll just use Ft cosine theta. The calculation, so substituting in the given data, including the fact that the force and the displacement are in the same direction, right? Same direction means our theta, or they have it as phi in the textbook. This is a phi. But theta is equal to 0 degrees. Okay, so writing that out, we have work is equal to Fd cosine of 0 degrees. So that's 40 newtons times the displacement, which is 0.5 meters, times the cosine of 0, which is 1. And that gets us 20 joules of work. Okay, so we can determine that the system on which the work is done to see which energies change. Because the crate's speed changes, there is certainly a change in kinetic energy, a change delta K in the kinetic energy. Now, if there's friction between the floor and the crate, and thus a change in thermal energy. So note that the force and the crate's velocity have the same direction. Thus, there's no friction. Thus, if there's no friction, then the force would be accelerating the crate to a greater speed, right? Because you're pushing in the same direction that the displacement is, but somehow your velocities are going down, right? So there must be friction involved. And that's what it says here, right? So the crate's slowing, so there must be friction and a change in thermal energy of the crate and the floor. Therefore, the system on which the work is done is the crate floor system, right? Because both energy changes occur in that system. So part B is, what is the increase in thermal energy of the crate and the floor? Well, we start with saying, well, our total work, which is our external work that we put in, this is the external work, must equal whatever the change in kinetic energy that we got out of it plus whatever thermal energy that we're losing. So we know that work is change in kinetic energy plus change in thermal, plus the change in potential, right? So let's go ahead and write that all out. Work is equal to change in kinetic plus change in potential, right? Because change in mechanical is kinetic and potential, plus the change in thermal energy. Well, it's just going across the floor. So we know that the change in potential is going to be 0, right? The gravitational potential is not changing, so that term goes away. We know that delta K, right, is going to be 1/2 m final squared minus 1/2 m v naught squared. Right, 1/2 m vf squared minus 1/2 m v naught squared, right? Because it's final minus initial. And our change in thermal energy, well, the n equals, so we're going back up to this equation here. We're going to plug in what we know about the change in kinetic energy, right? Because we're solving for change in thermal. So we'll take this and solve for the change in thermal energy. We get work minus 1/2 m vf squared minus 1/2 m v naught squared, where again the work is the work put into the system. So we can simplify this a little bit. say this is work minus 1/2 m, so we just pulled that out of each term, and we have Vf squared minus V naught squared. Alright, so we can go start plugging in values. So this is going to be 20 joules of work, because that's what we figured out was put into the system. And we can do 1/2 times the mass, which was 14 kilograms, times our change in squared velocities. So this is going to be final minus initial, so 0.20 squared minus 0.6. Oops. Squared. Right. And then you plug this into a calculator, and you get 22 joules, and this was the change in thermal energy. Alright, so our last topic is the law of conservation of energy. And this is a big one. There's a couple different ways that we can think about the law conservation of energy. First of all, the total energy E of a system can change only by the amounts of energy that are transferred to or from that system. Therefore, the work, again we'll call this the external work, that's put into the system is going to be our change in energy, and that's going to equal our change in mechanical energy plus our change in thermal energy plus our change in internal energy, or any other types of change in energy. And that just mentions that here. So the total energy E of an isolated system cannot change. And that's what the law of conservation of energy says. So it says that if you look at this change, look at this change, look at this change, it must equal 0 as long as there's no external work being done on the system. So in class, I give you a better way to write this. I think one that makes more sense. Essentially, if you have no external work being done on the system, the energy, the total energy at some point must equal the total energy at some other point. So for instance, I'll use a quick example. So let's say we have a roller coaster, and the roller coaster goes up, goes down, something like that. If I look at some point up here, let's say it starts at rest at this point here. Then it's released from rest, it goes down the hill, and then kind of goes up and down, up and down. Well, we know that the kinetic energy is going to be being transformed into gravitational and then back and forth and back and forth. So when it goes down into a valley, it's going to have more kinetic energy. When it comes back up, it's going to have more gravitational energy. So really, I can pick any 2 points, or I can pick these 2 points, I can pick these 2 points, I can pick these 2 points. Oops, I lost it. And it doesn't matter, right? The total energy is going to be the same. So the way I would write that is, let's say at point A, so you have your kinetic energy at point A plus your potential energy at point A is going to equal the kinetic energy at point B plus the potential energy at point B. Right? And if you have other types of energy, you have thermal energy, you include thermal energy on both sides. If you have internal energy, you can include that on both sides. If you have elastic potential, you can put that on both sides. So it really kind of molds to whatever you need. All right. So that's conservation of energy. So the last little topic that this chapter covers is power. So power is the rate at which energy is transferred by a force from one type to another. All right, so we talked about work and energy. Well, power is essentially how quickly that transfer is occurring. So if the amount of energy E is transferred in in a specific amount of time, the average power is given by this, which is essentially saying the change in energy is divided by the change in time is going to be our average power. But if you wanted to find what the instantaneous power is, we would have to use the derivative. Right? We're looking at some small change in energy, and we're looking at some small change in time. Now, if you look at your equation sheet that's given to you for these tests, they actually relate this to the work. So essentially, we're looking at a change in energy which is caused by external work that's done to the system. Right? So you see this. You'll see dW dt, which essentially means the same thing. right? Because for the energy to change, you need to do work, right? So this is essentially just saying a little bit amount of work in some little bit amount of time, right? To find what the instantaneous power is going to be. So if you had, for instance, if you had a function of work that's based off of, let's say, time, because that's what we're deriving it against, then we could take the derivative of that function, and that will give us what the power is at some specific moment in time. All right, that's it for this lecture. Make sure you check the Chapter 8 example problems lectures that has some of the example problems from the homework.